Hi, this is the fourth video of the series of video that I'm going to explain about quantum computing. In this video, I'm going to introduce Deutsch's algorithm. So first, let's ask this question. What is a quantum algorithm? A quantum algorithm is a series of quantum gates acting on a qubit or multiple qubits. For example, you're looking at the diagram that shows two qubit states are attached with a series of quantum gates. One is Hadamard gate and the other is CNOT gate. So you have to read from the left to right. You can see the two wires, and on the left end of the two wires I put cat 0, and this means that these two qubits are initialized at 0, 0, and H gate is the first quantum gate applied on the top wire, and the next I put the CNOT gate. Here the dark circle means it's the control gate and the target is denoted as the box here. So let's take a dotted line on each cases, each part 0, 1, 2, and compute the quantum state respectively. I'm going to label the qubit from bottom to top. So the bottom qubit is qubit 0 and the top qubit is qubit 1. So before I apply any quantum gate, which is psi 0 cat state, is 0 tensor 0. As soon as I applied Hadamard gate on the qubit 1, it becomes the linear combination of cat 0 and cat 1 tensor product with cat 0. And then let's apply the CNOT gate. When the qubit is 0 for the first qubit, I don't do anything. So 0, 0 stays as 0, 0. But look at 1, 0 state. The qubit state of the control qubit is cat 1. So I have to apply X gate on the qubit 0. So 1, 0 state becomes 1, 1 cat. Anyway, what is Deutsch's algorithm? So let's talk about the simplest function we can think of, which sends 0 or 1 into 0 or 1. Basically, there are 4 cases. You can classify these 4 cases into 2 categories. One is balanced and the other is constant. Let's say we want to find out which category this function is without knowing about the information of this function. All you can do is query the function. It means that you can throw in the binary value 0 or 1 to see what the output is. The question is, how many times do you have to query the function to find out which type the function is? You need at least 2 queries. You need to ask what is f0 and 1. So the Deutsch's algorithm can actually classify the function with a single query, which is impossible in any classical algorithm. So how does it work? We need an oracle in the circuit. What is an oracle? Oracle is a multi-qubit gate which consists of input register, which is on the top, and output register, which is on the bottom. And if you input cat X and cat Y, it outputs the cat X, which is same as the input state, but you change the output register. So here we use Y plus f of X. This plus is binary addition, which means that it only works with a binary number. When you add 0, 0 and 1, 1, it becomes 0. And if you add 1 and 0, it becomes 1. So this is how Deutsch's algorithm look like. So let's go through step by step. I'm going to separate this quantum algorithm into 4 pieces. So the first one, the psi 0 state, is initialized state, is 0 cat tensor 1. And the second one is applying Hadamard. When I apply the quantum oracle, I don't know the value of function, but I know what is going to be the input. So when I put 0, the output will be f0, and the quantum state of the output register is 0, because 0 plus anything is just the same thing. But when I add it to 1, then it changes its bit. So I'm going to denote hat as an opposite bit. So if f0 is 0, then f0 hat is 1, and vice versa. And you can do the same thing for the second part with f1. So and then what happens next? So I apply the Hadamard gate on the input register. I can group all this together with 0 cat for input register. So here are the long linear combination of quantum states in the output register. So take the last part of the previous slide and let's see what happens for each cases. For example, let's say if I have f1 that the value is always 0. Now this is the constant case, and look at the first linear combination, which is the tensor product with the ket 0. So f0 is 0, f0 hat is 1, f1 is 0, and f1 hat is 1. So basically, you get 2 ket 0 minus 2 ket 1. But however, let's look at the second part here for the same case when we had f1. So f0 is 0, f0 hat is 1, f1 is 0, 1 hat is 1. So what you get is ket 0 cancelled out with another ket 0 here for f1, and ket 1 we had here is cancelling with the ket 1 right here. So basically you get 0 on these parts. So if your function were f1, there is no chance you can observe 1 in the input register, only 0. So you can go over all these 4 cases, and when the function is constant, you get always ket 0, and when it's balanced, you always ket 1 for the input register. So based on your measurement outcome, the C, if it's 0, then you get constant. When it's 1, you get balanced. So we queried the oracle once, found out whether function is constant or balanced. So in this video, we briefly went through the Dutch's algorithm, how this works. In the next video, we're going to introduce another algorithm, which is called Dutch-Sosa algorithm. Thank you.